Welcome back to the Software Engineering Music Deep Dive into Python. Whether you're a seasoned Python developer ready to peek behind the curtain, or an ambitious programmer preparing for those challenging technical interviews where deep language knowledge makes all the difference, today's exploration is going to be something special. We're about to embark on a fascinating journey into the heart of the CPython interpreter itself, moving far beyond the familiar syntax and semantics to uncover the intricate machinery that actually executes your Python programs. This isn't just about knowing what Python does. We're diving deep into the how and the why of program execution at the interpreter level. Picture this. You have a simple .py file sitting on your computer. Just text, really. But when you run that file, an incredible transformation takes place. Today, we're going to trace that complete journey, step by step, from your source code, through its compilation, into bytecode, and finally, to its execution within the Python virtual machine. What makes this exploration truly compelling is how we'll uncover the beautiful interconnectedness of Python's design decisions. You'll see how choices made in memory management directly influence Python's concurrency model, how name resolution rules ripple through to affect performance at the bytecode level, and how this entire complex system is orchestrated by an elegant core evaluation loop. Feel free to pause, rewind, and absorb this material at your own pace. We're covering some seriously sophisticated computer science here. As always, you'll find additional resources and deep dive references in the description below. This is part of our ongoing Software Engineering Deep Dive series, where we don't just skim the surface, we dive to the very foundation of how these systems work. Ready to peek inside the Python interpreter and see the magic happen? Let's begin our journey into the heart of CPython. From source to bytecode, the compilation phase. Python's hybrid execution model. A common point of confusion is whether Python is an interpreted or compiled language. The most accurate description is that it employs a hybrid model. Python's source code is first compiled into an intermediate language called bytecode, which is then interpreted by the PVM. This two-step process is a deliberate design choice aimed at optimizing performance. The compilation pipeline involves several distinct stages that transform human-readable code into a format the PVM can understand: source code.py file. The process begins with a text file containing Python source code, typically saved with a .py extension. Lexical analysis, tokenization. The interpreter's first task is to read the source file and break it down into a stream of tokens. These are the smallest meaningful units of the language, such as keywords, e.g. def, if, identifiers, e.g. variable names, operators, e.g. plus, equals, and literals, e.g. 42, hello. This stage is analogous to breaking an English sentence into its constituent words and punctuation marks. Parsing, syntax analysis. The stream of tokens is then passed to the parser, which checks if the sequence of tokens conforms to the language's grammatical rules. It assembles the tokens into a structure known as a parse tree, or concrete syntax tree, CST, which represents the code's grammatical structure. If there is a syntax error in the code, it is typically caught at this stage. Abstract syntax tree, AST generation. The parse tree is highly detailed and includes syntactically significant but structurally redundant information, like parentheses. To simplify, it is transformed into an abstract syntax tree, AST. The AST captures the code's essential logical structure without the syntactic clutter, making it a more efficient representation for the next stage. Bytecode compilation. Finally, a compiler component traverses the AST and generates Python bytecode, a low-level, platform-independent set of instructions designed specifically for the PVM. To avoid the expensive overhead of this compilation pipeline every time a program is run, Python implements a caching mechanism. When a module is imported, the resulting bytecode is saved to a file with a .pyc extension. These files are stored in a subdirectory named dunder pycache dunder within the same directory as the source files. On subsequent imports, Python checks if a valid pyc file exists and if its modification timestamp is newer than the corresponding py file. If so, it loads the bytecode directly from the pyc file, bypassing the tokenization, parsing, and AST generation steps entirely, which significantly speeds up program startup and module loading. The existence of these pyc files serves as the most tangible evidence of Python's initial compilation phase, refuting the misconception that it is a purely interpreted language. Understanding bytecode, the PVM's lingua franca. Bytecode is the intermediate language of the PVM. It is a low-level, but not machine-level instruction set that is independent of the underlying hardware platform. This platform independence is a key feature of Python. The same pyc file can be executed on any operating system, Windows, Mac OS, or Linux, as long as a compatible PVM is installed. The bytecode instructions, often called opcodes, are simple commands that manipulate the PVM's data structures. Key categories of opcodes include stack manipulation. Instructions like load_const push a constant value from the code's constant pool onto the PVM's evaluation stack. Pop_top simply removes the topmost item from the stack. Variable and name operations. Load_fast pushes a local variable onto the stack. Store_fast takes a value from the top of the stack and stores it in a local variable. Load_global is used to load global variables or built-in functions. Arithmetic and logical operations. Binary_. Add pops the top two values from the stack, adds them, and pushes the result back onto the stack. Compare_op performs comparisons, like less than, equals, or greater than, on the top two stack items and pushes a Boolean result. Control flow. Call_ function invokes a function using values from the stack as arguments. Return _value exits the current function and returns the value at the top of the stack to the caller. The design of the bytecode instruction set itself offers a window into Python's core philosophies. The existence of distinct load_fast and load_global opcodes is not an arbitrary detail. It is a direct reflection of Python's name resolution rules, the LEGB rule discussed later, and their performance implications. The compiler, aware of the different lookup mechanisms for local and global variables, emits specialized opcodes to optimize performance. This demonstrates that abstract language rules like scoping have concrete, performance-impacting implementations at the lowest level of the interpreter's execution model. Inspecting the blueprint with the dis module. Python provides a powerful built-in tool, the dis module, for disassembling bytecode. This module translates the compact binary bytecode into a human-readable format, allowing developers to see the exact sequence of instructions the PVM will execute for a given piece of code. The output typically consists of 5 columns: the original source line number, the instruction's byte offset, the opcode's name, the opcode's argument, an index, and a human-friendly interpretation of that argument, such as the name of a variable or the value of a constant. The DIS module is an invaluable tool for performance tuning and debugging. It allows a developer to move beyond assumptions about code behavior and see the ground truth of its execution plan. For example, if a loop is unexpectedly slow, disassembling it might reveal that a variable is being accessed with the slower load_global instruction instead of the much faster load_fast. This transforms an abstract performance concern into a concrete, evidence-based analysis. It is also important to recognize that Python's bytecode is not static across versions. Recent versions of Python have introduced significant optimizations, such as the specializing adaptive interpreter in Python 3.11, which can modify bytecode at runtime to specialize it for different data types. The DIS module can be used to view these adaptive changes, providing insight into the ongoing evolution of CPython's performance strategies. Being able to use a tool like DIS to prove a hypothesis about performance demonstrates a sophisticated, evidence-driven approach to programming. The PVM as a stack-based machine. The CPython PVM is architected as a stack-based virtual machine. This means that it uses a stack, a last-in, first-out, LIFO data structure, as its primary workspace for performing computations. To visualize this, imagine a stack of plates. To compute an expression like 5 plus 3, the PVM would execute a sequence of instructions that manipulate this stack load_const5. A plate with the value 5 is placed on top of the stack. Load_const3. A plate with the value 3 is placed on top of the 5 plate. Binary_add. The PVM takes the top 2 plates, 3 and 5, performs the addition, and replaces them with a single new plate containing the result 8. The result of the operation is now at the top of the stack, ready for the next instruction. This stack-based approach significantly simplifies the process of compiling high-level Python expressions into a linear sequence of bytecode instructions. An expression tree from the AST can be traversed to directly emit a corresponding sequence of stack machine opcodes, which is a more straightforward algorithm than the complex register allocation required for register-based machines. It is critical to distinguish between the PVM's conceptual evaluation stack and the system's memory. While the PVM operates on a stack, this stack is a data structure that itself resides in the computer's main memory heap along with all the Python objects it holds references to. The call stack and frame objects. To manage the flow of function calls, the PVM uses a call stack. This is not the same as the evaluation stack. Rather, it is a stack of frame objects. When a function is called, a new frame object is created and pushed onto the top of the call stack. This new frame becomes the active execution context. When the function finishes and returns, its frame is popped off the stack, and control returns to the frame below it. A frame object, PyFrame object in CPython, is a rich data structure that encapsulates the entire self-contained execution context for a single function call. Its anatomy includes f_back, a pointer to the previous frame on the call stack. This creates a linked list of frames, which is exactly what is traversed to generate a traceback when an exception occurs. f_code, a reference to the function's code object, which contains the bytecode instructions to be executed, as well as constants and names needed by those instructions. F_locals plus a highly optimized C array that stores the function's local variables. This is why local variable access is so fast. It's a direct index into this array. F_globals and F_built-ins, pointers to the dictionaries that represent the global and built-in namespaces, respectively. F_value stack, the evaluation stack, the stack of plates used for computations within this specific function call. F_lasty, the last instruction index, which acts as the program counter, keeping track of the next bytecode instruction to be executed. F_block stack, a separate internal stack used to manage control flow constructs like loops and try, except blocks. This architecture provides a clean separation between a function's immutable definition, the code object, and its mutable execution state, the frame object. A code object can be thought of as a blueprint, while a frame object is the actual workshop built from that blueprint for a specific invocation. This is why recursion works. A single code object, blueprint, can have multiple distinct frame objects, workshops, existing on the call stack simultaneously. This separation also enables advanced features like generators, which essentially work by pausing execution and preserving their entire frame object, ready to be resumed later. The core evaluation loop ceval. The absolute heart of the PVM is its main evaluation loop, which resides in the ceval.c source file in CPython. This is effectively an infinite loop that drives the execution of all Python code. For the currently active frame object, the loop relentlessly performs a fetch-decode-execute cycle. Fetch. It retrieves the next opcode and its argument from the frame's bytecode array using the instruction pointer F_lasty. Decode. It uses a giant C switch statement to determine the action corresponding to the fetched opcode. Execute. It runs the block of C code associated with that opcode. This C code manipulates the frame's evaluation stack, local variables, or other state. Repeat. The loop continues to the next instruction, unless an opcode like return_value is encountered, which causes the loop to terminate for the current frame. This evaluation loop is the fundamental reason why Python is inherently slower for CPU-bound operations than compiled languages like C or Rust. Every single Python instruction, even a simple addition, incurs the overhead of this interpretive loop. Fetching an instruction, decoding it through a switch statement, and then executing a generic C function to perform the operation. In contrast, a compiled C program's addition instruction is translated directly into a single, highly optimized machine code instruction that the CPU executes without any intermediate interpretation. The ceval loop is the layer of abstraction that grants Python its dynamism and flexibility, but at the cost of raw execution speed. Efforts to accelerate Python, such as the specializing adaptive interpreter or just-in-time JIT compilers like PyPy, are all fundamentally aimed at reducing or eliminating the overhead of this very loop. Python's object model, mutability and immutability. All data in Python is represented by objects. Every object has three core properties: an identity, a type, and a value. The identity is a unique, unchangeable identifier for the object, which in CPython corresponds to its memory address and can be retrieved with the dot. id function. The type retrieved with the type function, defines the object's behavior and is also unchangeable. The crucial distinction between different kinds of objects lies in the mutability of their value. Mutable objects. The value of a mutable object can be changed in place after it is created without altering the object's identity. Examples include lists, dictionaries, and sets. Immutable objects. The value of an immutable object cannot be changed. Any operation that appears to modify it actually creates a brand new object with a new value and a new identity. Examples include numbers, integers, floats, strings, and tuples. This distinction has profound practical consequences. When a mutable object is assigned to multiple variables, it creates aliases, multiple names pointing to the same object in memory. Modifying the object through one name will affect all other aliases, a common source of bugs. Conversely, immutability provides safety and predictability. Perhaps the most critical consequence is in hashability. Only immutable objects can be used as keys in dictionaries or as elements in sets. This is because the lookup mechanism in these data structures depends on an object's hash value remaining constant for its entire lifetime. If a mutable list were used as a dictionary key, its contents could change, which would change its hash value, effectively losing the entry in the dictionary. The choice between using a mutable or immutable type is therefore a fundamental design decision. It is a contract that signals intent. Using a tuple instead of a list, for example, communicates and enforces that the collection of data is not meant to be altered after creation, leading to safer and more predictable code. Understanding the distinction between mutable and immutable objects in Python is fundamental to writing correct, performant, and thread-safe code. Here's a narrative breakdown of their core differences and when each type is most appropriate. Mutable objects. When you need. Changeable state. Mutable objects are those whose internal state can be changed after they are created. Common examples include list, dict, set, and byte array. In-place modification is possible. This means you can add, remove, or modify elements without changing the object's identity, i.e., the object remains the same in memory. When passed to a function, mutations inside the function affect the original object, since both the caller and the function refer to the same memory. Not hashable, and thus cannot be used as dictionary keys or set elements, because their values, and thus hash, could change, breaking lookup behavior. Not inherently thread-safe. If multiple threads access and mutate a mutable object, you must protect it with synchronization mechanisms like locks to avoid race conditions. Use mutables when you need to update the same object repeatedly, e.g., building up a result list. Performance demands avoiding the creation of new objects during updates. You're managing complex state, e.g., within a class or cache structure. Immutable objects, when you need safety and predictability. Immutable objects cannot be changed once they are created. Classic examples are int, float, str, tuple, and frozen set. Modifications actually create a new object, leaving the original untouched. This is why expressions like x equals x plus 1 with integers actually rebind x to a new object. Functions cannot alter them in place, which ensures the original value in the caller's scope remains unaffected. Hashable and safe to use as dictionary keys or set elements, since their value, and thus hash, is guaranteed not to change. Thread-safe by nature. Since no thread can modify their state, there's no need for synchronization during concurrent reads or operations. Use immutables when you want reliable behavior across scopes and functions. You need keys for dictionaries or sets. You're working in multi-threaded contexts and want to avoid shared state bugs. You favor functional programming principles or value safety over mutation. Memory management, a two-tiered system. CPython's memory management is a sophisticated two-part system designed to be both efficient and robust. Part A, reference counting, the primary system. The primary strategy for memory management in CPython is automatic reference counting. Every object in memory maintains a counter that tracks how many references, from variables or other objects, point to it. When a new reference is created, e.g., list_b equals list_a, the object's reference count is incremented. When a reference is destroyed, e.g., a variable goes out of scope or is reassigned to none, the count is decremented. The main advantage of this approach is its determinism. As soon as an object's reference count drops to 0, its memory is immediately deallocated. This means resources are freed promptly, without the unpredictable pauses associated with some other memory management schemes. However, reference counting has a fatal flaw. It cannot handle circular references. This occurs when two or more objects refer to each other, creating a cycle. For instance, if object A contains a reference to object B, and object B contains a reference back to object A. Even if all external references to this pair are deleted, their internal references will keep their counts at 1, meaning they will never be deallocated by reference counting alone, creating a memory leak. Part B. Generational garbage collector, the backup system. To solve the circular reference problem, Python includes a supplemental tracing garbage collector, GC. This garbage collector is designed specifically to detect and break reference cycles. It operates on the generational hypothesis, the observation that most objects in a typical program are very short-lived. This hypothesis allows for a significant optimization. The garbage collector divides objects into 3 generations based on their age, how many garbage collector cycles they have survived. New objects start in generation 0. The garbage collector runs most frequently on this youngest generation, as it is the most likely place to find garbage. During a collection, the garbage collector builds a graph of all objects in the generation and identifies islands of objects that are unreachable from the main program but are kept alive by internal cycles. These cycles are then broken and the objects are freed. Any object that survives a collection is promoted to the next, older generation, which is scanned much less frequently. This two-tiered system is a pragmatic engineering compromise. Python gets the primary benefit of immediate deterministic deallocation from reference counting for the vast majority of objects. The more expensive tracing GC is then used only periodically as a backup system to patch the specific weakness of reference counting by cleaning up cycles. The Global Interpreter Lock, GIL, the concurrency consequence. The Global Interpreter Lock, GIL, is a mutex or lock that protects access to Python objects within the CPython interpreter. Its effect is to ensure that in any multi-threaded Python program, only one thread can be executing Python bytecode at any given time, even on a multi-core processor. 1. The existence of the GIL is a direct consequence of CPython's memory management design. The reference counting operations, incrementing and decrementing a number in memory, are not atomic on modern CPUs. This means that if two threads tried to modify the same object's reference count simultaneously, a race condition could occur, leading to a corrupted count. This could cause an object's memory to be freed while it is still in use, leading to a crash, or to never be freed at all, a memory leak. The GIL is a simple, albeit coarse-grained solution to this problem. It places a single lock around the entire interpreter, ensuring that only one thread can manipulate Python objects and their reference counts at a time. This design has a profound impact on performance CPU-bound tasks. For tasks that are purely computational, the GIL acts as a major bottleneck. Because only one thread can execute Python code at a time, using the threading module for CPU-bound work provides no performance gain on multi-core systems and can even make the program slower due to the overhead of managing the lock. To achieve true parallelism for CPU-bound tasks, developers must use the multi-processing module, which sidesteps the GIL by creating separate processes, each with its own interpreter and memory space. I/O-bound tasks. For tasks that spend most of their time waiting for external operations like network requests or disk reads, the GIL is less of a problem. When a thread initiates a blocking I/O call, it releases the GIL, allowing other threads to run while it waits. This cooperative multitasking makes the threading module highly effective for improving the throughput and responsiveness of I/O-bound applications. The GIL is not a bug, but a historical engineering trade-off. It prioritized single-threaded performance and, crucially, simplified the integration of C libraries. This ease of creating C extensions was a major factor in Python's early adoption and success. The modern view of the GIL as a problem stems from the shift in the computing landscape toward ubiquitous multi-core processors. In response, there are now official efforts to make the GIL optional in future versions of Python, a monumental undertaking that requires a fundamental redesign of CPython's memory management and CAPI.25. The story of Python's concurrency model is a direct causal chain. The choice of reference counting made the interpreter non-thread safe, which necessitated the GIL, which in turn fostered easy C extension development, but now limits CPU-bound parallelism on modern hardware. Names and scopes. The LEGB rule for name resolution. When Python code uses a name, such as a variable or a function, the interpreter follows a strict set of rules to determine which object that name refers to. This search order is known as the LEGB rule. The four scopes are searched sequentially: L, local, the innermost scope containing names defined within the currently executing function, including its parameters. This is the first place the interpreter looks. E, enclosing, the scope of any enclosing functions. This is relevant only for nested functions closures, allowing an inner function to access names from its containing function scope. G, global, the scope of the current module. Names defined at the top level of a .py file reside here. B, built-in, the outermost scope, which contains all of Python's built-in functions and exceptions, like len function, str function, and key error. The interpreter searches these scopes in the LEGB order and stops as soon as it finds a match. This is why a local variable will shadow a global variable with the same name. This rule is not merely an abstract convention. It is physically implemented by the compiler. and has direct performance consequences. When the compiler analyzes code, it determines the scope of each name and emits a specific, optimized bytecode instruction for its access. For a name in the local L scope, the compiler emits the load_fast opcode. The PVM executes this instruction by performing a highly efficient lookup at a fixed index in the current frame's f_locals plus C array. For a name that must be found in the global G or built-in B scope, the compiler must emit the load_global opcode. The PVM executes this instruction by performing a significantly slower dictionary lookup in the module's global or built-in namespace dictionaries. Therefore, the common performance advice to prefer local variables is not a vague guideline. It is rooted in the fact that the LEGB rule is translated into concrete bytecode instructions with fundamentally different performance characteristics. That's it for today's video. If you found this content enjoyable, please remember to like and subscribe for more. Good night.